Right, this is the 1999 paper that I gave you last night to do. Now we're moving on from looking at momentum before and momentum after to looking at something that's called changing momentum. But the same principle applies. I mean, normally for momentum style problems, this is the equation that you would apply. That basically tells you that this is the momentum before the collision and then that this is the momentum afterwards. Momentum is always conserved, so those two values should be equal. And you can use that to figure out, say, values of v here or here if you know what's happening beforehand. But here what we're looking at is actually changing momentum, but it's really just a rearrangement of this equation here. So if we're looking for the momentum of the first vehicle, the changing momentum of the first vehicle, then it's going to be just by simple rearrangement. That will be your momentum, changing momentum of the first object. And then by simple rearrangement again, it'll be m2v2 minus m2u2. This will be your changing momentum afterwards. That's pretty simple. It's kind of like acceleration, v minus u, a change in speed. It's very similar to that. So that's really what the logic that you need to apply for this question. The first part there, part A, state the law of conservation of linear momentum. It's that the total momentum before a collision is equal to the total momentum after a collision. Now it's not simply good enough just to write that. You would have to make the description fuller than that to say that the total momentum before a collision is equal to the total momentum after a collision. The second part is when you have to start applying your usual sort of logic. So you've got the 75 kilogram mass, which is A, I think, in this case. That one here. That's your 75 kilogram mass. And it's travelling at 0.82 meters per second. And then you've got this mass B, which is 50 kilograms, and that's initially at rest. So 0 meters per second. So this is stationary. Now that's your collision beforehand, before the objects strike each other, and then afterwards they move off separately. So they're not joined together this time. They are moved off separately. So 75 kilograms, its velocity reduces to 0.4 meters per second, and then the 50 kilogram mass now has a velocity of 0.63 meters per second. Now these are both in this direction. So that's what I would do before you tackle anything. What is it, Kev? So not 75? Sorry, 0.75 it is. Does that mean that's 0.5? Okay. So before you tackle any of these types of questions, what I would do is just draw out your diagram like that. Then you've got to calculate the momentum of the 0.75 kilogram mass. So that's going to be m1v1 minus m1u1. That's going to be the change in momentum, because m1u1 is your momentum before, m1v1 is your momentum after. So it's going to be 0.75 times 0.4, because that's the velocity afterwards, minus 0.75 multiplied by 0.82. So does that give you is it 0.03? No, 0.3. 0.3 minus 0.615. So is that minus 0.315? And momentum is kilogram meters per second. So that's the change in momentum of the 0.75 kilogram mass. Then look at the 50 kilogram mass. it's going to be M2 V2 minus M2 U2, which will be 0.5 times 0.63 minus 0, and that will give you 0.315. So that proves what it's looking for in the question, is that the change in momentum is identical, it's just that it's in different directions. So one of them is slowing down and one of them is speeding up. So basically this one is slowing down, that's why it's negative, and this one is speeding up. So one has a positive change in momentum, the other has a negative change in momentum. The second part is looking for the kinetic energy to prove whether the collision is elastic or inelastic. So you're basically going to use EK equals a half mv squared for this. So that's the kinetic energy of one object, but remember, for a collision, whether it's elastic or inelastic, you need to know how much kinetic energy you have in total before and how much you have in total afterwards. So there are a couple of ways we can do this. I'm going to do it the slightly shorter way. So the EK before will be equal to a half m1u1 squared plus a half m2 u2 squared. So that's going to be a half times 0.75 times 0.87 squared plus a half, in fact, times 0.5 times 0. So that's basically going to be 0. So this will come out at being 0.25 joules before. After, EK is going to be equal to a half m1v1 squared plus a half m2, sorry, m2 that is, no it's not, m1, m2 v2 squared. So a half times 0.75 times 0.4 squared plus a half times 50 times 0.63 squared will come out as being 0.16. So you've obviously got EK being lost there somewhere, so you need to make a final statement at the end to confirm whether it's elastic or inelastic. So EK is lost. So collision is inelastic. Exactly. And that's it.